Okay, in this video, in the next few videos, actually, we're going to be talking about Stokes' theorem. Today, we're going to talk about, or in this video, we're going to talk about Stokes' theorem. In the next videos, we'll look at some examples. Okay, so now Stokes' theorem is the Green's theorem, but for surfaces. So let me say that again. Stokes' theorem is the Green's theorem for surfaces. So Green's theorem is technically about surfaces, but it's about surfaces that are just in the xy plane. Stokes' theorem is about surfaces that could be in 3 dimensions. Okay, so curved surfaces. Like if you look at the first example, the surface that we're going to be looking at is the top half of a sphere. It's a hemisphere. Okay, Green's theorem doesn't apply to that. So let's look at what it says. So if S is a nice surface, if S is a nice oriented surface in R3, and DS is its oriented boundary curve, then we have this relation. Okay, so let's talk about this. So let's look at this. We have an integral on the left-hand side. It's a double integral on the left-hand side of a derivative. So this is the curl of a vector field. It's not in bold, but it should be. So let me just put a vector field over it, or a vector over it, an arrow over it, I guess. So we're doing a double integral of a derivative. Curl of f is like a derivative of the vector field on the left-hand side. On the right-hand side, we have a single integral of the vector field. So again, this is why we call this a generalization of the fundamental theorem of calculus. Okay, so now let S be a surface. So this is a surface that is curved in R3. Okay, so it has, and it's oriented. So it has an orientation vector like this. Okay, this is the normal vector. So in other words, when I say orientation vector, I mean a normal vector. Okay, so this would be like maybe upward orientation. Then you could have the vector on the other side would be downward orientation. Okay, so that's what we mean by an oriented surface, meaning there is an orientation given. And the boundary of S, that's a curve, that is the oriented boundary. So how do you do this? Well, it's gonna be similar to what we talked about with Green's theorem to determine what the direction of the curve is. Okay, so when we look at this boundary curve, this could be the orientation. It could have the counterclockwise orientation, or it could have the clockwise orientation. So the way you figure out whether or not you have a counterclockwise or clockwise orientation is you walk along the boundary of the curve with your head sticking in the same direction as the normal vector, and you stick your left arm out. So if your left arm is pointing over the surface, you are walking in the oriented boundary. The orientation of that boundary then has the same orientation as the orientation of the surface. If you stick out your left arm and it's not pointing over the surface, then you are walking in the opposite direction. So if you walk along the blue line with your left arm sticking out, if your head is going in the direction of the normal vector and you walk along the boundary with your left arm sticking out, then your arm is going to be pointing that way, which is not over the surface. But if you walk along this direction, counterclockwise, with your left arm pointing out, then your left arm is going to be pointing over the surface. So if this is the surface and it kind of has this upward orientation, then the oriented boundary curve has counterclockwise orientation. Okay, and this is something that's going to be tricky to kind of figure out on some problems. But basically, you just have to do the work. You just have to do practice and think about it. And Dr. Yaskin has some other great ways to think about this in his book that I encourage you to look at because he has really good illustrations that I'm not going to be able to replicate here. Okay, we're already like we're clearly at the boundary of my ability to draw. Okay, one other thing I want to mention is let's compare this with Green's theorem. Okay, so remember curl is technically, so if we look in 2 dimensions, if we have some vector field, F1, F2, this is technically not defined, the curl is technically not defined in R2, but if we just add a third component that's 0, we can define the curl of that vector field. And actually, instead of using F1 and F2, let me use P and Q to make this consistent with the notation. So this is I, this is J, this is K, this is partial X, partial Y, partial Z, then P, Q, 0. Okay, So what do we get when we compute the curl here? Well, the first component is going to be the partial derivative of 0 with respect to y, which is 0, minus the partial derivative of q with respect to z. But p and q are both functions of x and y. So the first component is 0. The second component is going to be negative the partial derivative of x of 0, which again is 0, minus the partial derivative of p with respect to z. Again, that's 0 because p is only a function of x and y. And finally, we're left with the derivative of q with respect to x. So the partial derivative of q with respect to x minus the partial derivative of p with respect to y. Okay, so notice that if the surface happens to lie in the xy plane, then the thing that we're going to be computing here is just going to be the surface integral of the third component of that vector field, which is qx minus py, which is exactly that. So really, Green's theorem then is a special case of Stokes' theorem. But it's nice just to call it something different because it's kind of something very specific. Okay, in the next couple of videos, we're going to look at examples using Stokes' theorem to do some integrals.